In this common experience, the motion of something moving through water creates all kinds of movements. This hodgepodge of motion is close to chaos. On a small scale, it is impossible to predict what will happen to an individual patch of water. With some simplifying assumptions, however, we can create a simple mathematical model of the behavior of a fluid. This picture shows an aerodynamic shape that allows fluid to flow smoothly around it. The shape is said to be streamlined, and the lines indicating the smooth, parallel movement of fluid are called streamlines. Before we can create a simple mathematical model, there are 4 simplifying assumptions that we must make. 1. The fluid is non-viscous. 2. All particles of fluid making up a cross-section of the tube have the same speed. 3. The fluid is incompressible, meaning the volume of a fluid element does not change. 4. The flow is laminar. Each particle moves parallel to every other particle, and there is no rotation. For our discussion, we'll look closely at this curved pipe that is large at the left end and small at the right end. Fluid moves through it from left to right. Notice that the flow is laminar. As the fluid moves into the end of the pipe with the smaller diameter, its flow remains laminar. The streamlines move closer together but are still parallel. It may be apparent to you that the velocity of the particles must be faster in the narrow end of the pipe than at the wide end. At some velocity, the laminar flow breaks up. This is evidenced by the development of eddies and swirls in the flow. This turbulent non-laminar flow has more friction than laminar flow and requires more energy to flow through the tube. As the flow becomes turbulent, our mathematical model becomes inaccurate. For this unit, we will limit ourselves to a close look at the laminar flow of a fluid. A slug of water moving from the left to the right stretches out to be longer in the narrow end of the tube. The volume of the slug of water at the left is equal to the area of the wide end times the length of pipe containing the slug. At the narrow end, the slug has a different cross-sectional area and a different length. But it is the same slug of water, so the volume of the slug of water in the narrow end is equal to the volume in the wide end. Just as the volume of the slug at both ends is the same, its mass at the 2 ends is also equal. The velocity of the fluid in the slug is equal to the length of the slug, L, divided by the time, T. There's another quantity that will be useful. It is called the mass flow rate. The mass flow rate is the mass of fluid M that flows past a point in a given time interval. It equals the mass divided by the time. Since mass equals the density times the volume, then the mass flow rate is equal to the density times the volume divided by the time. The volume equals the area of the pipe times the length of the slug. Substituting this into the mass flow rate equation above allows us to say that the mass flow rate equals the density times the area times the length, all divided by time. And length divided by time is the velocity. So the mass flow rate equals the density times the area times the velocity. We've paved the way to an understanding of the flow of fluids. In the pipe, the mass flow rates at the left and right ends are the same. In addition, the density is the same at both ends. This allows us to derive the equation of continuity, which states that the area times the velocity of the fluid at one end equals the area times the velocity at the other end. As before, the subscript 1 refers to the slug of water when it is on the left, and the subscript 2 refers to it when it is on the right. The product of area times velocity is called the flow rate. Its units are cubic meters per second, which is equivalent to volume per time. Thus, it is also called the volume flux. There are many common applications of the equation of continuity. Suppose that the diameter inside a fire hose is 15 centimeters and the diameter inside the small end of the nozzle is 5.0 centimeters. If the water travels through the hose at 2.0 meters per second, how fast will the water leave the nozzle? Try again. Correct. Here's a problem that involves the physics that you learned near the beginning of this course. If the hose without the nozzle were aimed straight up, the water would only rise about 0.5 meters. How high above the nozzle would the water travel if it were shot straight up? Try again. Try again. Correct. No doubt you've noticed that as water runs down from a faucet, the diameter of the stream decreases. Having just been reminded about the effect of gravity, you might guess that as the velocity of the falling water increases, the area also decreases. The water from a faucet with a diameter of 3.4 centimeters begins its fall at 1.0 meters per second. How fast is the water falling when the diameter of the stream is 1.5 centimeters? Try again. Correct. When blood flows through arteries, it moves quickly because of the pressure behind it. When the blood enters a capillary, its rate is much slower. The sum of the areas of all the capillaries is much greater than the cross-sectional area of the aorta that comes directly from the heart. The human aorta may have a diameter of 1.5 centimeters with a blood flow of 20 centimeters per second. Individual capillaries have diameters of about 8 times 10 to the negative 4 centimeter. But there are billions of them. An estimate of the total cross-sectional area of all a person's capillaries is 2,100 square centimeters. Given this information, how fast does blood move through a capillary? Correct. The flow of blood through each capillary is very slow. This allows more time for the exchange of materials between the blood and the surrounding tissues. Imagine a fish tank that is 2.2 meters long, 1.6 meters wide, and 0.90 meters tall. The water in the tank is renewed every 10.0 minutes by a pipe that carries fresh water at 1.0 meters per second. What must the radius of the pipe be? Try again. Try again. Correct.